Hi everyone, welcome to Math Spellbook. I'm your host Peter, and basically we are going to continue on with Taylor's Classic Mechanics today. This will be the last day for this week, so hopefully you guys are ready to get your preparations in order, whether you're working on math or whether you're working on any type of projects that you're doing on the side. Hopefully my stream gives you like enough I guess productive energy to continue on whatever it is that you're doing, studying for, or just basically just making, you know? You could be like doing code or something on the side, and that's also fine. No, I don't think so. I don't think we'll be able to do all the problems, because there's like, how many? 30 something? Yeah, like over 30 something problems. Yeah, like over like 50 problems in here. I don't think we'll be able to complete the book. And I think we spend a lot of time like on the first section. So we were only working on space and time. I mean, it's a nice title for the book. I mean, for the section. But how you doing, Slender? Yeah, maybe I should have just jumped around instead of just working down the line. But yeah, let's just get started, shall we? Oh, here's an interesting problem. Prove that the vector product of is distributed. That is... Oh. Okay. Prove that the cross product... Okay. So I guess 17 seems to be an interesting problem. Woke up early today to do linear algebra. Oh, cool. So I guess that's the best part of your day so far. Yeah, because like the second study session, I might not work from this book. Maybe I'll just do some simple like calculus problems just to get some review in. Because I remember Mavort yesterday said it's probably better for me to review calculus and linear algebra. So I thought I would do a little bit of that in the second study session. So I guess we can start doing let's see, number 17. It's a 2-star problem, so it might be a little bit difficult. So we have to prove that the cross product is distributive. So actually we shouldn't write this part. What part of linear algebra were you studying, Slender? Meaning that... Oh, this should be fun. I feel like we're gonna do a lot of component notation here. So x plus xv yu plus yv, and then zu plus cv, and then we're given r, which is take the cross product of those. So let's just do the first side first, because I think that'll be, I mean the right hand side first. I think that would be easier. So we will do r x y c r, and then r y u, and then z u. So therefore, the first part will be y u y r z u minus z r y u. Actually, kind of like when we do this, it's sort of like a little bit of linear algebra, like the first part of linear algebra, now that I think about it. So now we're doing CR XU minus that is J plus here, then we'll do R cross V, which would be and V which would result in dang, my handwriting is very, I think it's when I'm writing like basically like stuff that I want to get done, I accidentally scribble too much. Plus CR XV minus X written that down. this together. This will be fun. And that plus that's not J. It's I. Because we have a lot of big space. Timer and I forgot to take my model off. So where was I? Oh yeah, right down these, then that minus let's see. I mean, we can combine was like, why is there a T there? And I'm like, no, that's Z. So I'm thinking we can combine the expressions with sign out. At least not for this case. Make it a little bit easier to deal with. extremely tedious. Yeah, I thought this problem would be interesting, but at the same time, it's like I'm either making it very more tedious than it should be, or I'm like, is it supposed to be this tedious? Hey Tyrion, how's it going? What's the best part of your day so far, my friend? You can make it shorter. Yeah, I could probably make it shorter. That's the thing with me, is like whenever I work on a problem, I usually think of like the way that I'm so used to it, but then I don't see that the pitfall of it could be like, oh, it's extremely tedious. Because what we're trying to prove is that the cross product is distributive. So we got basically our RX cube. You know what? Let's erase this. I don't think we need that right now. Okay, so this is basically what we got. Plus. Prove one component, then you can argue it is the same as the other two. Yeah, that's what we're supposed to do. Since you can rotate the indices. Yeah, thank you for your suggestions, Tyrion. Like, if you guys have any suggestions on how I can solve a problem, but, like, you're not sure whether to give me hints, just ask, like, need a little help. Just type in need a little help. Because sometimes when you guys, like, I know you guys are trying to help, but at the same time, like, sometimes, like, I feel like I'm cheating myself whenever, like, you guys are being helpful. That's not your fault, it's just my pride, I guess. Because I feel like I'm supposed to be learning, and that's for, I guess, like, that's for the stream's benefit as well as my benefit. At the same time, like, sometimes, like, when you guys give suggestions, either you guys are way ahead of me and I'm not following the logic that you're trying to display because I haven't gotten there yet, or, like, I'm probably, like, on that breakthrough, but I haven't had it popped into my head. If that makes any sense. Because we have our... So this time, might as well go with the simple approach, I guess. Just show that these are alike. So basically, we are given just put UV on the bottom. I don't want to rewrite everything. UV. I know that looks like it's sort of like a, what do you call it, a subscript, like for a tensor product or something, but I'm like, I mean a tensor, but I don't want to like write like the whole thing like U plus V or something like that. That'd be more tedious than it should be. So we'll start off with Y minus They are circular. You should look at... It's easier to argue to say that the result is... are the same since they shift indices. It's pretty much like we can just like basically have it in this form. So I think we've already proven that. I mean, in my head I feel like we've done that already, given like how much we've like written it down. Okay, second part, prove the product rule. This is more thinking about vector calculus. Gotcha. Maybe we'll probably do that in the next section. Let's put T over here so it just makes it easier to see. I don't know why I put parentheses there. Didn't need to do that. To make it bigger. Okay, the fun part. be the product rule, each one of these. So then basically the derivative of each one will I already, like, since I've done the one with the dot product, like, I'm already so used to, like, actually seeing what's gonna happen. So basically this d over dt is gonna basically distribute, and then basically all these will have to be the product rule. I don't feel like I need to write that down. So the cross product of ds plus dr dt. Yeah, because like if you do it with the other way, then the other way is just basically going to be the derivative of s, and then basically it's just going to be like merged together, which creates the same thing. I mean, I already see it in my head, but like I don't think we need to like continue on with that. It'll be like overly tedious. What do we got here? Oops. What's 18? The three vectors A, B, and C are the three sides of a triangle ABC, with the angles up. Oh, okay. In figure, prove the area of the triangle is given by the three expressions. The cross product. Oh. Okay. Use the equality of these three expressions to prove the so-called law of Steins. Or I should say signs. Why did I say Steins? Oops. Interesting problem. I haven't done problems with laws of sines and cosines in like a long time. Okay, prove that the area of the triangle is given by one of these expressions. Well, let's see, vector A, vector B. I wonder if I can copy this. I mean, it would be nice. Like, take this whole entire triangle, but I guess I have to do it from scratch. Make another line here. Yeah, that looks really nice. And I think they have a head here, tip here, and right here. This is vector A, vector C, vector B. We have A, B, and C. It's beta, alpha, and gamma. Okie dokie. Oh, hello. We have an unwanted guest. Bye-bye. I just hate it when that happens when I'm streaming. It's like, a bot just came in. Bye-bye. Even their name is self-explanatory. Unfriendly Apple. That was unfriendly. Okay. Alright. So we have to prove that the area is one of those. And I forgot to click into my tablet so that we can get some writing done. not parentheses. Absolute value. Okay. So technically, we would have something like this. If it's the cross product, that's supposed to be the magnitude of it. So. This up, then go through the daily routine. Okay. Probably, actually, Tyrion, probably during break time, I'll take a look at the video you posted. And I'm actually glad that you guys are not abusing the link posting privileges. Because, like, if the channel gets bigger and people start putting random links in the chat, I would feel bad for you guys that have been so helpful posting links in. Because then, like, you know, like, some people can abuse that, but, like, I'm so glad that you guys are so nice. Just posting stuff that is actually useful for all of us to learn and to grow together. Yeah, so that would be the new vector. And then that divided by a half. Wow. Actually, seeing how bad my handwriting is, I'm kind of glad that I didn't get into teaching. Because I don't know if my students would be able to read my handwriting. They would probably tear me apart. It's like, your handwriting is not legible. I don't know how we can take notes like with this. So they said that. Oh yeah. Right. So we would have to do. We'd have to square the whole thing here and do the square root of this thing. Get a half. Because it's a new vector, and the distance of the vector. Oh yeah, because the cross product, it basically expands out, like, basically the two vectors that are crossed, they make a new vector that goes, a new normal vector that goes up or down, depending upon which, what numbers we're dealing with. So if it creates that, then basically the area, because then we just made one new vector that just goes up from the two vectors that we made. Because I'm trying to get the geometry in my head. I know I'm not writing anything down, but it's like, I feel like I'm having like this epiphany type of moment. Because I'm thinking, like, I know like math, I don't know like how do you prove it like rigorously mathematically, but I guess like when I'm thinking of the geometry of it, like just regular like two-dimensional, well technically it would be three-dimensional because we have a normal, I mean we have a cross product because there would be a vector that's pointing up from both B and A in this case. And then with that, that would be the length. And then when we calculate the length of that vector, and then divide it by half. For some reason, I'm just visualizing that perpendicular normal vector we made from like the plane of the two vectors. For some reason, I keep like thinking that, okay, you take the distance of that, but then you divide that in half. And now I'm like wondering, how does that give you the area? Unless we're thinking about triangles, which I think we are, because we're supposed to be thinking about triangles in this case. I don't know, like if you guys think my logic is completely off, like let me know. Or if I'm getting close, you can basically say you're getting close to it. You're getting, like, that's a good way of thinking about it. You can also say stuff like that to me too, if like I'm getting close but you don't want to give me the full answer. That would actually be better for me, because then I can get to the answer myself there. Yeah, because I'm like, now I'm asking the question, why is it that the cross product divided by a half gives you the area of the triangle, at least? I mean, I know with a triangle it's like half base times height, but wait. So so vector A and vector B, and then if you take the cross product, you take a vector that's like perpendicular to those two. Excuse me. These questions are pretty interesting, because now they're trying to make me now they make me think about how to visualize, in addition to like how to get to, I guess, the logical thought process of like how to actually look at vectors in a different way. Because I'm so used to just doing vectors, like adding them, subtracting them, multiplying by a scalar by them, doing the cross product, the dot product. Now it feels like I'm actually trying to delve deeper into like the essence of what makes the vectors work geometrically. I guess for me, whenever I took math in class, I'm so used to doing just the calculation part. But when it comes to the actual, I guess, like getting the essence of what it is that the operations that I'm doing, I think that is like the thing that I've been trying to like contemplate. Yeah, because like, so basically, so my thought process is that we have to make, well, not make, but show that is equivalent to base times height, at least for the triangle case. So what part of it would be the base and what part of it would be the height? Because the cross product will produce a normal vector that's like perpendicular to both. So, well, I should write normal vector. I'm just writing it out so I can basically have something visual to see. So what is it in the dot product that gives us a base, and what is it in the... What is it in... I mean, not dot product. What is it in the cross product that gives us the base, and what is it in the cross product that gives us the height? I mean... the equality of these expressions to prove the so-called Stein's, why am I saying Stein's? It's signs. It's signs that, is... I think with the law of signs you can like interchangeably flip them around, right? Like basically like sine of alpha over A as well as like A over sine alpha. Because I remember Googling it and I saw it in both variations. I always thought it had to only be one type of variation, but it could be both. But what is it that makes this length? I mean, if we go back to our sketch, see, we have A and vector B. So we have an, I'm just gonna draw a dotted line here. We'll just call this like n for our normal vector for the cross product, or maybe I just put it straight because it's supposed to be perpendicular, but it could be popping in or out of the page. But it's supposed to be the length of the cross product between the two vectors. Why does that give that area? You know what? I think that's also within, I think I remember seeing it in the vector, Student's Guide to Vector and Tensors book I've had. Let me see. Drag this down here because I think I remember seeing something like that. Let's see. Basis vectors, cross product. Okay, yeah, this is something I remember seeing. Let's see, the direction of the cross product. The length of the cross product equals the area of the parallelogram formed by a... The length of the cross product equals the area of the parallelogram. Okay, so I understand why it's half because it's a triangle, but the one thing is that why is the cross product an area? I mean, the length of it anyway. That's the one thing I'm not getting. One way to picture the length in this, yeah, we got the figure here. Just as the dot product involves the projection of one vector to another. That one I remember. In this case, the magnitude of the cross product between the two is proportional to the area of the parallelogram formed with these two vectors as adjacent sides. As you may recall, the area of a parallelogram is base times height. In this case, the height of the parallelogram is the magnitude of B sine, and the length of the base is A. That makes the parallelogram equal... Okay. Huh. So the angle between the two vectors is 0 or are parallel or anti-parallel. The cross product between them is 0. And as in between, okay. And then they show you like different variations of like the unit vectors. Okay. Huh. Oh, okay. So basically it is this, right. So it said this is the length. This is supposed to be the height of the parallelogram, which is B. And then, oh, okay, okay. Now I see what they're talking about. Interesting. Very interesting. So what was the dot product again? Like, what did they say it was geometrically? The projection, right? Yeah, it's supposed to be the projection. Okay. I know that was a lot more reading than writing and solving problems, but you know, that's also part of our journey in the stream. So, I mean, I'm kind of glad that I actually looked up this, because I remember there was something geometric about it, and I think that's what I lack when it comes to vectors, is to be able to like associate them with, I guess, like geometric properties. I'm so used to vectors just being arrows, and like the operations involving vectors, I'm so used to doing computations with it, not like doing things like geometric. Well, I guess, I mean, we did learn something at least. So that's why it's basically, so A and B are sort of like giving off the vibe of, how should I say it? Gives off the vibe of basically like acting as like a stencil, like sort of like a drawing on the plane, even though the cross product of it is just basically popping off the page or popping into the page. Like when you actually do the calculation on the plane itself, like basically like the sign of like whatever vector you're doing it to. And I guess it's half because it's supposed to be a triangle. That's why it's not a parallelogram. I mean, that's how I can explain it like leniently to myself. I learned I'm sore from swimming as a sine alpha over alpha as alpha goes to 0. Very funny, very funny. Yeah, so yeah, there's like a lot of stuff that we haven't done in this first chapter. We spent so much time just on vectors. Maybe I should have just titled Vectors with Classic Mechanics. Which probably shows that I have a lot to do with involving vectors, especially with the laws of sine and cosine. Let's see if there's a fast problem we can do. Because we've done problems that were just kind of tedious. But then again, the further you go down, the more tedious the problems get. Excuse me, guys, sorry. Prove that any two vectors A and B, the length is less than or equal to A plus B. Hint, work out and compare it with, explain why this is called the triangle inequality. I think you do this in real analysis. Oh, break time already. Okay, I'll put my model up. So, what video did you send?
What's going on, smart people?
Oh, Andrew Dawson. Yeah, I remember I remember watching his stuff. I think he's like mostly working. I don't know if he's still on his internship or he's like now working on like mainly being a physicist now. Because I haven't seen his content in a long time actually. We'll do what you suggested, Tyrion. We'll watch some of this. So I think I'll move our math chat to the side so that we can see. And then I'll just scroll up here. I'll move the chat back when we get to doing something else. So I think I'll just... I don't think the music's too much of a bother. We'll just turn it down a little bit for you guys so you guys can hear it.
Well, today's video is all about the cross product. We all have our favorite way of calculating them, that we had to memorize some stuff in order to do it. Today I'm going to show you how to do it a different way, a more formal way, using what's known as the Levi-Civita symbol. And before we get into that, I'm going to show you the way that I learned how to do a cross product. We're going to see what we get, and we're going to see that it matches up with the Levi-Civita.
If you guys can hear the video, I can turn the music off.
So I'm assuming you all know what a cross product is, but just for good measure, if we have some vector A and we're crossing it with some vector B, what that gives us is a new vector C that is perpendicular to both A and B. And the way that I was taught to evaluate these kinds of things is as a determinant. So I have my basis vectors at the top. Let's use Cartesian here, EY, EZ. And then we have the components of the vectors here. So AX, AY, AZ, BX, BY, BZ.
Okay.
And I was always taught to cover up the column of the basis that I'm working with right now and the row of the basis vectors, and then evaluate the determinant that's left over. So in this case, this would give us AYBZ.
For me, I just looked at the formula and I was like, how can I make this simple in my head so I can remember? I always forget that is actually the determinant.
The x component of this new vector, so that's our E sub x. And just by the way, if I write like E sub x, that's the same thing as x hat, that's the same thing as E sub 1, that's the same thing as I hat. I don't really care what you use to talk about your basis vectors as long as we
I'm so used to I hat, J hat, and K hat.
Especially when it comes to indexing with numbers, with integers, that's going to be important later on. Okay, and then I also know that for some reason there's a minus sign that comes up for the next one. And I cover up the column, cover up the row, and I get AX BZ minus AZ BX. And that's going to be my E sub y component, and so on for E sub z. And that works. I mean, you get the right answer, but there's memorization of knowing like what to cover up, and then you tack on a minus sign, and it's a little weird. And there's a better way of doing this, and now we come to introducing what's known as the Levi-Civita symbol.
Okay, let's see what this is.
What this object is, it's epsilon ijk, and it's defined to be 1 for cyclic permutations.
Okay, what the
hell does that mean? Cyclic permutations. Well, I can be 1, 2, or 3. So I equaling 1 corresponds to the x component. I being 2 corresponds to the y component. And I equals 3 is z.
Okay.
Okay, so if we have ijk can all be 1, 2, or 3. So if we have ijk being 1, 2, 3, so I being 1, j being 2, k being 3, that's what's called a cyclic permutation, and that means this symbol here would be a 1. If you think of it this way, to where this is a 1, this finger is a 2, and this finger is a 3, we can rotate it such that the 2 becomes the new first number, in which case the next way around would be 2, 3, 1.
Oh, I think I remember reading about this.
Permutation. So we would get 2, 3, 1. Likewise, we could also get 3, 1, 2. If it helps, if it's a little bit easier to think of it this way, just write 1, 2, 3, 1, 2, 3, 1, 2, 3 over and over again. This works, shift by 1. This works, shift by 1. This works, whatever helps. So if you come across any of these combinations, this symbol is 1.
Okay.
This symbol is -1 for anti-cyclic permutations.
Alright.
Meaning, well, if it goes backwards, so if we get 3, 2, 1, or 2, 1, 3, or 1, 3, 2. So if these are the combinations of IJK, the symbol is -1. Lastly, the symbol is 0 for anything else. Typically what this means is if any of the indices repeat, meaning if we have like 1, 1, 3, or 3, 1, 3, or something like that. If any of them repeat, the symbol is 0. Alright, with that being said, let's define our cross product. Well, here, this whole determinant, this whole thing that's going on right here is the component, it's the x component of our new vector. This is kind of similar to how we're about to define the cross product in terms of the Levi-Civita symbol, because we're gonna define the component of the cross product in terms of it. So if we want to find, here's A cross B, if we want to find the ith component of this, so if I is 1, we're talking about the x component of this cross product. If we want to find the ith component of A cross B, that is defined as this Levi-Civita symbol. I'm going to give myself a little bit of space, you'll see why. Okay, so here we're keeping track of I, that's the index we care about, which means even though we have these JKs here, they have to go away at some point because our final answer just depends on I. The way of doing that is that means we're going to end up summing over J and K. So we got JK, and then it's going to be the J component of A times the K component of B, and we are summing over J and K. That is a pretty weird notation, I'll admit, but let's see what that means. So let's do a special case. Let's say we are interested in, say, the X component. Why not? In other words, we want to know what A cross B 1 is. So I is 1. So again, that is equal to sum over J, sum over K. These quantities all go from 1 to 3.
Okay.
Epsilon 1 JK, right? Because we know that I is 1 now. AJ BK. And now we just need to add up every possible combination of J and K. What's going to end up happening is that most of these combinations give us this result, where the epsilon IJK is going to give us a 0. Most of the terms don't contribute. With this example where we're calculating E sub x, we're going to brute force our way through the entire thing, and then when we calculate the next term, we're going to speed it up a little bit because we'll see what kind of symmetries there are. And we'll also make some assumptions that obviously we're going to be summing over the repeated indices and stuff like that. But let's go ahead and do this. So if we're summing over J and K, that means that the possible combinations are that this is equal to, let's start with 1. 1, 1, 1. So that means J is 1 and K is 1, so that's A1, B1, because these are also J and K, plus epsilon 1, 1, 2, A1, B2, plus epsilon 1, 1, 3, A1, B3. And you see how this is kind of monotonous, and right away we see that all of these so far have a repeated index, so they're going to go to 0, but you know, just to be thorough. Plus, let's do epsilon 1, 2, 1, A2, B1, plus epsilon 1, 2, 2, A2, B2. I'm doing this in a weird order, I know, but I'm just trying to make sure I get them all. Plus epsilon 1, let's say 3, 1, A3, B1, plus epsilon 1, let's do 2, 3, A2, B3, plus epsilon 1, 3, 2, A3, B2. How many do we have so far? We got 1, 2, 3, 4, 5, 6, 7, 8. I think we're missing 1, which is 1, 1, 1. This one's gonna be fun. Plus epsilon 1, 3, 3, right? Probably the one that we're missing. Yeah. A3, B3. Okay, so this is a lot of bookkeeping, but let's see what cancels. Here we have epsilon 1, 1, 1. These indices cancel, so this term goes to 0. This one has repeated indices. This term goes to 0. This one 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 does not. This one does not. And this one goes to 0. So the only two surviving terms are these ones right here. And let's take a look at this. So epsilon 1, 2, 3, that's a cyclic permutation.
Hey, Famish.
So that means that this symbol is 1.
Yeah, basically
so
Tyrion sent us a video to write cross products more effectively and less tedious.
A2, B3, because it's 1 times that. And then we've got 1.
But what's the best part of your day so far, Famish?
1, so it's minus A3, B2. And just to go to the older convention where we were talking about like Y's and Z's and stuff like that, that tells us that A cross B, the X component of this vector, is equal to AY BZ minus AZ BY. And if we look up here, we got AY BZ minus AZ BY. Perfect, it works. A lot of that was super thorough and redundant, and it wasn't very necessary. That's never what I would do if I was actually using this formalism of calculating a cross product, because it's unnecessary. What I would actually do, which is what we're going to be doing for this next case, and actually before we do that, let's go ahead and distribute this minus sign that we calculated for e sub y. So this is the same thing as AZ BX minus AX BZ, just so
doesn't look too difficult. Yeah,
make things a bit more clear.
Because I was so used to writing it the typical way that you would learn it. I didn't learn about this type of notation.
B2, so it means I is 2 now, and we're not going to go through all this because we know if there were 2 terms that survived here, that would be really weird if there weren't just 2 terms that survive here. So let's go ahead and write this out. You guys already know that we're going to be summing over J and K, so that's a bit of a more cumbersome notation. So we're just going to assume that we're summing over J and K. So this is equal to epsilon 2 JK AJ BK. And we know that if any of these 2 indices are 2, the epsilon is going to go to 0, right? So let's not go through that. We're smarter than that, which means that one of these has to be a 1 and one of these has to be a 2. Okay, so that means that this is equal to epsilon 2. Let's just do 3, 1. Let's do that case first. That's going to be A3 B1 plus epsilon 2 1 3 A1 B3. This is a cyclic permutation, so that is equal to A3 B1. This is anticyclic, which means that it's a minus A1 B3. In other words, that is equal to AZ BX minus AX BZ. And is that what we got up here? It sure is. Awesome. So this way, once you're comfortable with the method, once you understand that you're summing over the indices that don't show up over here, and all of the terms that have common indices are going to go to 0, once you've got that down, this becomes very fast. This becomes very fast, and you don't have to memorize anything. Now, you might argue that you have to memorize what the Levi-Civita symbol is, and that's true. That is true, but it is an actual mathematical object that pops into your life more than just
simplified expressions with exponents.
Yeah, mechanics quite a bit. It comes up with a lot of tensor analysis. Whereas the convention that you might be used to for just the regular cross product, that's only helpful for your definition of the cross product. It doesn't extend to anything else. So this is worth knowing because it pops up in other places. But that's going to do it for this video. I think I've talked about this enough. I hope you get the idea. Maybe see for yourself if you can calculate the third component and see if you get what you would if you did it my way or your normal way of calculating the cross product. Let me know in the comments section if you found this video helpful, and I'll see.
Okay, that was very interesting. Thank you for sharing that, Tyrion, if you're still in the chat. Yeah, that's actually a pretty interesting method to actually like doing that. I think we're gonna change it up now, so let me just change the title. We'll do so we're gonna do calculus slash, yeah, I think just calculus 2 review. Whatever we're gonna review, it's like up for debate. I'll put like first part classical mechanics, or like vectors in classic mechanics, and calculus. So we're gonna go into a little bit of calculus, or review anyway, for me at least. This time I'm practice until I feel comfortable moving on, since I didn't for the last 2 subjects. Oh, okay, that's fair. That's fair. Okay, let me see if I can find a book that we can use. Let's see. Let's try by, like, even though it's like a hard book, it's still my favorite. Calculus 4. Oh, you know what? Since we are doing vectors, there is a vector calculus book I can try out. Let me just move chat right here in the middle, back where you guys fit. Well, it's good that you're actually doing some math, Famish. Actually, for my gaming channel, I don't know what I'm gonna post in my gaming channel today, because I'm gonna be streaming on that channel too. I'm thinking about maybe playing like maybe Fortnite or something. I haven't played Fortnite in a long while. Well, I did play Fortnite last night, but I haven't done it on stream in a while. So before we get started, I just will use the restroom real quick. So I'll be right back, guys. Alright guys, I'm back. Let's turn on the study timer and let's begin. So this is a new book. I mean, it's a new book for me because I haven't read it. So I guess we'll just start, because we already know quite a bit about vectors. So let's just... Because the first part covers vector addition, scalar multiplication. I think that's like the basic stuff that you learn when you start learning vectors. Displacement. So we sketch the vector. Find the displacement vector. Let's see. What is this chapter called? Vectors in 2 and 3 dimensions. more about vectors. Let's see what is in here. So they talk about unit vectors. Oh, they actually show you the symmetric form. And I think this is where they talk about the parametric version of a line. Yeah, the parametric version of a line. Yeah, I remember this. What else do we have here? Oh, there are markings in this book, but that's fine. Write the basic vectors using the standard basis vector for... I think we know how to do that. It's like the I and J and K version of those. Show that the two sets of equations are actually represent the same line. Okay, that's actually an interesting question. We could probably try to do that one. Okay, so 20. Oh, that 27 didn't look right. Okay, so 2 over 3. And just put and over here, and goes -10. So, I think the first one, if you wrote this as a parametric line, so let's just put line 1, then we have the original vector, the original point being, okay, plus t of, so I believe it's like minus, so that's supposed to be vector 2, 1, and then 0. Now if we write the second line, the vector we have is, or the original point is 14 and 10, and then plus t. Then again, if you take 2 out of there, then we are left with -3, or actually -2. If you take out -2 from there, then you're left with 3, 7, and 5, which is the original starting point. Actually represent the same line in because wait, hold on. Is the bottom the vector or is it the top? I'm pretty sure the top is like the vector that's minusing it, right? Let's see, the symmetric. Let's see, the original P. Yeah, it is the original point. And I'm pretty sure that I saw that in my No Bullshit Guide to Linear Algebra book. That's how I remembered it. So they both have the same starting point if you were to do some fiddling around with it. Oh no, wait a minute, hold on. Because it's supposed to be minus, right? Yeah, it's minus, so then these have to be negative. Yeah, they're all negative here. So the thing is that how are they the same line? I mean, if you did a little trick, you can basically like maneuver it so it's like they're the so minus. I mean, they have the same starting point. That's a start. That's one similarity they share. Oh wait, did I pass it? Yeah, here we go. Because it says show that the two sets of equations are actually represent the same line. But the one thing is that how do I represent it like that? That's the one thing. Do I have to do it in this form, or do I have to do it in another form? Because we also have a z component here. Maybe I have to see how they did it here. Determine where the two intersect. So this is the symmetric form. So these are the intersection problems. What is this example? Let's see, from Euclidean geometry, there's Let's find the parametric equations of a line through the points. Let's see. Because I mean, writing out as like the writing it parametrically doesn't really reveal much. I mean, for them to represent the same line. I mean, visually it doesn't. What is it that I'm missing here? Maybe I'll try the other calculus book that I had in mind. Because I don't want to be spending too much time thinking about one problem like I usually do. I'll just let my mind like detach from it a little bit and then do something. There we go. My favorite calculus book. Actually, my first one, actually. Integration techniques. Let's do trig substitution. I haven't done this in a long time. So, just drag this up here. Okay, so how do we do this again? Trig substitution. Involving integrals. Here we go. Involving integrals 1 plus sine of a. So whenever x minus squared aim. Okay, so whenever a is in front, it's either sine or tangent. Whenever it's x in the front, then it's secant. Let's see how they do the first example. Let's see the area. I found something to read if you prefer about. Let me just. I'll just favorite that. I'll put that in my bookmarks so I can keep it as a reference. Thank you, Tyrion. I'll definitely look this over. Yeah, I remember reading about this in my my student's guide and vector and tensors guide. I remember reading about this notation. I didn't really pay that much attention to it. I probably should have. But thank you for sending that. Much appreciated. Okay, where were we? Oh yeah, getting back to trig substitution. Actually, this is the one I haven't gone back to in a long time. I have to actually like remember how to do this. So let's see. Verify the area of a circle with a radius a is pi a squared. Okay, so then take a out. Okay. basically change. The thing of it is that you have to change the parameters. Where's my? Oh, there it is. Yeah, it is useful for proofs. Oh, okay. Yeah, trig subs. Yeah, yeah, it's trig subs. We were working on a problem with vectors before. Basically, the problem is that prove that these two symmetric equations are part of the same line, or actually are the same line. But my brain was like not allowing me to actually like access what is it that I have to do to make a clever trick to that. So I feel like I'll just put down the problem and just move on to do something that I have to practice. Because usually like that's what happens. Like if you're working on, like you start with the hard question. Like I learned this later. I wish I'd learned this in school, actually, or during when I was in school, is that you do the hard questions first, and then like once you get stuck on the hard questions, you just do the easy ones, and once you get the easy ones done, sometimes the hard questions just like kind of you feel relaxed because you're doing the easy ones, and once you've done the easy ones, then sometimes the hard ones like they sometimes form connections in your brain. So so the thing to note, let's see, sign substitution. So we got 16, so we can like reduce that. Because I think the one thing I forgot. Oh, thank you for the follow. Oh, that's an interesting one. Popo. Popo 1 2 3 4 5 6 4 5 6. If you're in the chat, thank you for the follow. You actually became our 50th follower. Thank you for the follow. I really appreciate it. If you're in the chat, what's the best part of your day so far? Oh, make one of them equal to t. You end up with the parametric equation. Like, are you talking about which PDF software I'm using, or which writing software I'm using for writing stuff? I want to be the the square root of 2, both. So the one I'm using for writing is Miro, like it's spelled M-I-R-O, and the one for PDFs that I'm using is Okular. I think that's how you pronounce it. So yeah, I'm using both of those. Those are the ones I'm using. But what's the best part of your day so far, Popo? If you don't mind me calling you that. And what got you to give the follow? Like, are you really into math, I'm guessing? So let's see. Oops. Didn't mean to zoom in on that one. Let's see. Evaluate, then we do this, then we do that, then we do this, and do that. Simplify. I need to see what they do when they have actual define parameters, because I know you're supposed to change the theta. You're supposed to change the parameters from x to theta. Okay, so this one, what is this one? From 2 to, okay, yeah, so we need this. I want to actually see what happens. Integrate contains the expressions, right? Okay, using the reference triangle, we can express them as okay, so yeah, we're given these. Where's Where's the one they allow you to... Okay, here we go. Evaluate this. Yeah, because I know you're supposed to change the parameters. Let's see. And then... So you change that so from x plus 2. For example, we change the variable with u. X plus 2. Oh yeah, because it's in the denominator. So x plus 2 plus... Oh, okay. So basically with the x values here, yeah, because like it's 6 and... Okay. Alright. I changed my mind. I want to be the I to the I follower. Nice. Yeah. I studied civil engineering in first year and I wanted to watch math. Oh, nice, nice. Okay, I probably should do some problems because I spent like a good couple minutes just reading. Okay. Oh, cool. They go through each, so it's... So we'll do number 7 because I gotta actually get used to doing trig substitution, so... Okay. So for this one... you have to change this. So it would be like sine of theta. So I'm guessing x has to take the place of that one. Right, because then square root here. Which is 25 minus 25 sine of theta squared. And I think for these parameters, so in this case, we'll just put theta because that's what we're doing it to. So no. Wait a minute. My brain is like really not computing here. Okay, like we're not gonna do the parameters yet. Because sometimes when I do u substitution, when there's a definite integral, I always forget to like change it sometimes. I know you should. You're supposed to. 1 minus sine. Oh yeah, right. I forgot. You have to do a little trick with dx is equal to because x is supposed to be this, right? So then yeah, because then you're supposed to get like 5 times cosine dx. Yeah, because then that will be like that, so. side. And then we have cosine squared down here. That leaves us with just 1. Dx is equal to theta d theta. No trick yet. You take the derivative. Okay, so now we have the parameters for x, which is from 0. So that's the x parameters. Now, because it's going to result in theta. So now theta has to have new parameters to it, I think. Meaning, yeah, I'm actually glad that I'm actually getting back to this, because now I'm actually realize how much I'm lacking in this one. Actually, like when I was taking calculus for class, like when I was taking Calc 2, when I went back to college to do this, like this was actually this is the one I picked up very quickly. I think the one that I got stuck on the most was a series. Yeah, series and the washer and the disc method. Those are the ones, and the cylinder method. Yeah, those are the ones that I would get stuck on the most. I mean, I'm missing something. I just don't remember what it was. How'd they change that with you? These are not definite. Where's that one I saw? Oh, here it is. Okay, we got here. But they only did U substitution here. Equals U plus X plus, Okay, so for X in this case, oh wait a minute, hold on. Nope. I'm mixing things up here. Because what they picked for you was 2 to the X. So in this case, What did you type in, Tyrion? Series are less do this and get the answer, and more of come up with the answer and test it. Yeah. Yeah, I know we have to make a right triangle, and basically, like, if it's supposed to be, because if it's sine, then basically it's going to be like on this side. Well, first, I should probably just write out. Yeah, because then it would just result in that. Yeah, because these things would cross out. And then we left with 1. Now we just have to write the actual parameters here. The book is called Calculus for Scientists and Engineers. That's the title of the book. Let's see. Sine of theta is equal to x over, which means that the opposite side so that means like this parameter which gives us 5/10 a half. That's 0. So we're just left with theta from a half to a 0. Leaving us with just a half. However, in this case, it's just the inverse of both sides. Oops. Yep, I overstepped with that one. Yep, I overstepped. I forgot the sign. So it's like sine of, so the first one, well actually it's just going to be 0, so sine of 0, then basically theta will be equal to that would equal to 0, or I mean different variations. Because the first one will be 0, and then the next one it will be so, and then it will be lead to a half. So we still have 0 on the bottom, and then we'll just put I for the initial, and for the final we have a half for that one. So sine equals a half. That would be like theta would be yeah, I think that's it. Yeah. So 6. There we go. There we go. I forgot the sign. So pi over 6. Now, do we have to change it back to x though? I think we have to change it back to x. Because originally the problem was... yeah, the problem was originally... this. And if we draw a triangle like this, this would be theta. And the hypotenuse would be this. And then the sine of trying to like remember, because like I remember doing this like long time ago, because I remember every time when I did this on a test I would always draw this triangle. I would always like, it was a good way for me to check it. Only if it is an indefinite integral. Do you need to sub back? No, I don't think so. Let me just check. Because it looks like in the problem they basically just like do theta and then basically solve it for theta. Which I think gives the answer anyway, so probably you don't have to like resubstitute, like put x back in. So basically, like, yeah, I think it was because, like, when it's indefinite, that's when you draw the triangle to see if it makes sense. I have to actually jump back in to see the triangle so I can better remember. Yeah, so... oh yeah, A is supposed to be the hypotenuse. Okay, so I gotta remember these triangles, so... tangent, yeah, because so tangent is basically sine and cosine. Yeah, so to divide that, yeah, it would basically be that. Secant is, oh, secant is this one. So, okay. Alright, yeah, it's taking me a while to actually get back into this routine. I think it took me a while to get back into the routine of doing trig integrals when I did that last night. Hopefully the next one I can do really quickly. Probably next week I'll do like more calculus problems. That way I can like get better at them. I know I have been putting this off for a while. Okay, so x is going to be equal to 3 sine theta, and dx is going to be equal to cosine theta d theta. Then, just for a good measure, theta will be equal to sine. That way we can just get it done a little bit quicker. Yeah, we'll just leave it that way, so that way we can be better prepared. So final and initial. So obviously that one's going to be 0. This one would be half again. Okay. Which means... yeah, because then... yeah, then... no, that's actually what's inside. That's what's inside. So if it's a half, then it's going to be this. Okay. Alright. So we got the parameters. And then we just write down the good stuff here. But then it's not going to be the same as last time because we got 3 to the, so it's going to be the square root of 9 erase that. 9 sine of square. That 2 is too big. Hopefully we can get this done before the buzzer goes off. 3. So the thing is that we got this 3 in here. That's gonna cause some issues. I mean, we can remove it. One way or another. But then it would look like a totally different integral, though. Hate it when I change it to my eraser and I can't bring it up like I always do. Let's see, and then take the square root of 9. And then cancels on the top right. Yeah. Let's see, 9 to the 3rd power, no? I think we can just factor it outside of the parentheses. So I think it's fine. I think that allows for that. So I think we're okay in that regard. That's actually a really good question, but if the math is wrong, then I'll learn from that. So we're left with sine, and then to the 3rd power. Oh, gotta write those parameters. Write those parameters again. then we're going to be left with cosine to the third. Yeah. No, actually it would be cosine to the 6. Yeah. Cosine to the 6th power. Yeah. Cosine to the 6th power and cosine over like that. Oh, looks like our time is up. Well, even though I just basically read a bit, like, more in this study session, it was still pretty, like, productive, I think. I mean, it did get me back into trig substitution. I think we're gonna do more trig substitution next week, because I feel like I have to actually regain stuff. Like, Tyrion, I really thank you for your help, though. I really appreciate it. I know, like, for you, it's probably like you're watching a spectator sport. It's like you're telling me to do stuff and everything like that, but at the same time, like, you know, like, just relax. You can just relax and sit back. You don't have to like tell me exactly what is it to do next, because for me it's like I'm just trying to, like, do it on my own mainly. But when I look at the chat, I see you're just telling me, like to do certain operations, and I get it, because like you want to see me progress, and I get that. So I think that will probably be it for today's stream, guys. Hopefully you guys enjoyed that, even though basically it was just me, like, reading through and, like, just basically banging my head against the table. We'll probably get back to this problem next week, or maybe I'll do it on my own time, and then we'll basically practice more on calculus. So let's see if there's anyone streaming today. But, like, first of all, thank you, Popo, for, like, being the 50th follower. Unfortunately, I don't have anything special I can give you. I would love to, but I don't have anything special to give you. But thank you for being the 50th follower. Whether we make it to affiliate or not, like, you know, hopefully we get the email about that. I mean, I do have another Twitch channel, so I'm not too like overly concerned about it, but it would be nice to actually make a little bit of streamer money just to do math for you guys. And actually, when I do math for you guys, it empowers me more. But yeah, so if you guys really enjoyed this, be sure to follow, give me a sub on my, be sure to give me a follow on this channel if you love math or physics, or if you just want a productive stream to keep you occupied, to basically work on the stuff that you want to work on. You can just basically give me a follow, and I'll be like your little background noise for that. And if you're watching this on YouTube, please subscribe to my YouTube channel. I will type that in the chat for you guys in Twitch, so that you guys can actually subscribe to my YouTube channel if you miss any part of the vlog, any part of the stream for today. Like, say if you pop in for, like, the beginning, and then basically you just drop in and it's like, oh, like, I missed it, and it's like, no problem, we'll just do that. yeah, I forgot. Yeah, like, I guess when it comes to fraction exponents, we forget that, oh, you take the square root and then you basically, like, multiply it by the top. But that's actually, like, something I forgot. Like, sometimes I forget basic algebra. And also, if you guys want to keep active on, like, chatting about math or whatever, yeah, you can join our Discord server. I didn't even have to type it out. Sorry. And if you guys want to actually tune into my video game channel, where I play video games, you can tune into my Uncle Talk's Twitch channel. I play games there. Probably tonight I'll play, like, some I guess some shooter games, I guess, or something like that. Maybe I'll do Fortnite or Stranova or something like that. It depends on my mood. I sometimes, like, switch games, like, every, like, hour when I stream there. But yeah, so let me just type in Don Does Math is streaming. I mean, he's doing a video game, but we'll give him a hello, because sometimes he stops by the channel. So if you're watching this on YouTube, please drop a like and, you know, comment down below on like what I can do to improve the stream, or maybe like, you know, what problems I got wrong or what I can do to update my mathematical techniques, because I know you guys are a lot smarter than me when it comes to doing math problems or maybe physics problems as well. But if you're watching this on Twitch, you know, thanks for tuning in. We're gonna commence with the raid, so let me just give you the raid message so you guys can copy and paste that if you like. And we're gonna raid into Dawn Does Math. So yeah, I know I have to do that too, actually. I have to do that book too, actually. Okay, here we go. We're beginning the raid now. So I will see you guys on Dawn Does Math's channel, and always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys on Dawn's channel. So take care, guys. Bye-bye.